Hey everyone, in this video I just wanted to go through and maybe just show you some more examples of what differential item functioning looks like. And like we said previously, it's really a difference in the uh, probabilities. So the probability of correct response given theta, so the conditional probabilities. And that is dictated entirely by the item parameters, right? So these item parameters for group one, and as you see here for group two, they dictate these item characteristic curves or category response curves. And these item characteristic curves really just model the probabilities of correct response. And if I kind of highlight that, you can see that's just the p-value for the first group, which is kind of on the left over here, and then the second group, the red group, is over here on the right. So I just wanted to kind of play around with this a little bit. Certainly encourage you to do the same, just to get an idea of what kind of diff we're talking about here and what things look like. So I'm just going to put some values in here. Here you can see that we have a little bit of diff on the B parameter alone. You can see it right there when you look at the numbers. These are the two B parameters here. And you can also see it when you look at the graph. It's a uniform diff. This item always favors the blue group. And again, the way you know that, you either go up from 0 and see you have or some other number on theta, it doesn't really matter where, and see that you have a higher probability of correct if you're in the blue group than the red group for a given theta. Or you can kind of go from like a 0.5 or really any of the numbers over here and go straight across and see that it takes more theta to get that same probability in the red group than it does the blue group. So blue group's advantaged, red group is disadvantaged. And the extent to which we have diff and the magnitude of diff will dictate what that advantage looks like. So something like this, you might have a relatively large amount of diff. I think most people would consider this, pretty big. And that would be kind of huge. And that's going to be based on those item parameters, again, because the probabilities are based entirely on the item parameters. The underlying formula is the same in the two groups. So that's B parameter diff. Again, it results in uniform diff. You can change that around as much as you want. Take a look and see what it looks like. That went kind of crazy. Let me try that 0.5. And then you've got also the A parameter diff. And we can simulate that here a little bit by changing that around. And that gives you the non-uniform diff. So you can see that's going to vary as well. And we've already looked at in this semester's, the lower your A parameter, closer to horizontal that line gets. It's always going to have a little bit of an S shape to it, unless it's exactly 0 for the A parameter. But it's going to look more and more kind of like a horizontal line. And the higher the A parameter gets, the more and more it's going to look like a step function. In other words, it's really low, and then it jumps all the way to really high. And of course, one thing we didn't really talk too much about, but you can have both of these things, right? So you can have various types of A and B parameter diff together. They don't need to be the same. This would be, really some kind of unholy coincidence of like both A and B parameter diff that's enormous. This item will be, extremely problematic. More often than not, you're more likely to see things that are more like, 0.8, maybe a 1.2 for the A parameter, and something, more like, I don't know, like this or something. I mean, it's usually much more modest than what we're just looking at there. But I wanted to show you just a few examples of that in the two-parameter model. You can see what it looks like. You could do the same for the three-parameter model. It's just, you'd have an asymptote there that's lower, and you could modify that one as well. It would just, move the bottom part of the graph over here, move that up a little bit with the guessing parameter. I also wanted to extend that to the polytomous case. Let me make this a bit bigger here. And what I've got graphed here are the BRFs, the boundary response functions, for two groups in the graded response model. So it's a little bit busy. I apologize for that, but that's part of showing it to you. If I make these two lines identical, that sort of hides one set of line. We essentially have the same situation here. We've got two groups, and they've got a set of, I got one A parameter per group for a single item. Again, this is always looking at one item. And you've got a series of B parameters that we get, and we saw that in the last homework assignment out of R. And again, the GRM, graded response model, is it's an indirect model, so we get these boundary response functions first, and then we translate that into category response curves. So the thing that's a little different about the graded response model is that we have obviously 4 of these instead of 1 of these. And so the nature of the diff can take on sort of a lot of different forms. So for example, You can still have sort of uniform and non-uniform diff, but you're much more likely to have non-uniform diff in this scenario. So if I make all these B parameters for group 2 like 0.5 higher than they are for group 1, then you can see then everything moves over by a relative constant. But that doesn't have to be that way, and that's a little bit rare to see actually. So I'm going to set these back to equal. And you can even have things like this, in which you've got a situation where um, only one boundary response function is higher in one group than another, and that'll affect the probability of responding with each category. So what you might see in this case, the probabilities of putting a 1, 2, 3, and are all the same, but then the groups differ in whether they put a 4 or a 5. And again, that'll look a little more intuitive when we look at the category response curves. But I wanted to show you the boundary response functions first. You can have a situation where you might have something like this, where, is that what I wanted to do? Let me try that again, make that 2. Where, the red group in this case is kind of got one lower and one higher, and that would be, if I make this even more extreme, might be a case where people use the middle points of the scale, or maybe a 3, identically, but one group is more likely to be centrally tended than the other. So in this case, the red group obviously needs less theta to move from a 1 to a 2. So and also needs more theta to move from a 4 to a 5. So the red group, would you expect to be a little more central tendency in that group, whereas the black group, you would see less central tendency than the red group. Again, you can have differences in the A parameters as well, and that just further complicates things. So you can see it can get quite complex. So when you're talking about graded response model, you're a little bit less likely to talk about uniform diff or non-uniform diff. You're more likely just to talk about sort of the nature of the diff, and it's more likely to be non-uniform because even if the A parameters are identical, you can still have non-uniform diff just through differences in the B parameter. But I wanted to show you what that looks like as well before we move on talking about the category response curves. And let me make these everything bigger here a little bit. And the category response curves, you can see here, I've made them slightly different just so you can kind of see what they are outlined. And I quite like this graph. It's nice and color coded. So I've got the same colors representing the same categories. So 1 would be the lowest response option for both groups. 2 would be, or yellow would be the response option 2, blue 3, green 4, and dark blue 5. And then one group is the dotted line group, and one group is the solid line group. And group A is solid line, group B is dotted line here. And I'm sorry, I was inconsistent with my labels down here versus what I've got up here actually. So this graph again is very handy because it makes really clear the way groups differ and how they're using the response scale. And as you can see here, these item parameters, they're pretty similar, especially, for these and this one, but they differ just a little bit, and especially that B2. And so the B2 parameter, you see that the dotted line group is more likely to put a 2 than a 3, whereas the solid line group, it's got a little bit more of an even spread there, kind of an even distribution between 2s and 3s than you see with the dotted line group. And just like before, we could mess around with this a whole bunch. We could maybe make this a much more uniform kind of thing. So we could just shift everything to the right. We could shift everything over to the left if we just kind of added a constant to one group to get the other group's B parameters. A lot of different things we could do here. We can change the A parameters and it'll flatten things out, but the general pattern should still hold. I like it with the higher ones because you can see the curves a little better in that. But again, I hope this gives you some indication of the nature of differential item functioning, what it looks like in IRT, what it looks like when you're really down in the details and you're looking at the way people use each given category in the response options. Okay, now that you got a little bit of better idea of what diff is and what we mean by differential functioning and item response theory, I wanted to go back really and discuss a little more about where that comes from and what diff looks like in practice. And I mentioned this item, we'll start with a little bit earlier on, but it's a classic item that has diff. And the nice thing about this item is actually pretty clear where the diff comes from. And so this is a word analogy item where decoy is to duck as A, net the butterfly, B, web to spider, C, lure to fish, D, lasso to rope, D, E, detour to shortcut. And the answer is lure is to fish. And this item has diff by gender. And as you can probably tell, one of the things this item is measuring is not just your verbal reasoning ability, but also your knowledge of hunting, specifically for ducks, and fishing. And if you didn't know what a fish lure is, you're not going to get this item right. So this is an item that showed diff by gender because historically at least, there's pretty big differences by gender in the activities that young men and women would have. And so young men were more exposed to this notion of decoys for duck hunting and lure for fishing than women were. So it's a good, nice textbook example because it's fairly obvious where the diff comes from. There's a good chance a good review of the items beforehand might have even caught this, but it's a kind of a textbook example in this case. And I mentioned something earlier, but I think this example kind of makes clear too that what we mean when Camille and Shepard talk about diff as multidimensionality. And I think it's important here to mention that multidimensionality, we're not talking about a secondary factor that would come out in a factor analysis. So if you were to factor analyze a bunch of items, you wouldn't usually see a clear factor come out as a second factor and say that's where the diff is or that's where the diff comes from. What they mean by this is really, and I referenced it earlier, but it's really more talking about a systematic source of variance that impacts the two groups like we defined it earlier. So in the last example, that secondary factor is hunting and fishing knowledge, and it impacts this one item. It wouldn't impact other items on the test, so it would never come out in a factor analysis or anything like that, but it's multidimensionality with respect to that it's not only just verbal reasoning that impacts performance in this item, it's also knowledge of the secondary topic in hunting and fishing. Another example that we can look at that's cited sometimes, this is on a first grade test, so this is for small kids, and the items mark the thing that is neither cat nor dog, and another item is mark the thing that is unopened. And here they saw racial diff, and in this case, the researchers concluded that it was in fact bias and not just diff because of cultural differences in the use of negatives. And so the idea was African American or Black populations are more likely to use negatives in a different way, and maybe a slightly more unorthodox way than were white examinees here in the first grade. And so if this were, perhaps on the bar exam, they might have concluded that this was in fact relevant because at that level, you could argue that, kind of using language in the textbook way or the more traditional way might be relevant for the job. But for first grade work was not relevant. And so they concluded that this was bias. I think a review of this previous item would also be considered bias, right? It's hard to argue that hunting and fishing knowledge is in fact relevant for verbal ability measurement. So one other kind of thing I wanted to touch on a little bit is oftentimes speeded tests will show diff. And in this case, it's actually kind of clear where the secondary factor comes from. When you introduce speed, and we haven't talked about this much in the class, when you introduce speed to a test, you've changed the test from something called a power test to more of a speeded test. And I used to teach this in psychometrics. I don't know if you've exposed to it or not, but a pure power test would usually be something like an unlimited test where people would have all the time they want. Speed's not a factor at all. And it's just based on knowledge and ability. And so your score reflects the underlying trait of knowledge and ability without respect to any kind of speed. On the other hand, and these tests are a little bit rare too, you usually see them for things like clerical work. We have the pure speeded test, and the speeded test, by the way, is what's used for clerical work, not the power test. And in a pure speeded test, typically you have a number of items, a large number of items, and a relatively short amount of time to do the items. But the items are really simple. They're simple enough that if you gave people unlimited time, almost everybody would get every item right. It's usually basic clerical things, maybe reading charts or tables, things along those lines that are not meant to be challenging at all, but really the test is meant to measure the speed at which somebody can work. In a pure speeded test, you wouldn't even score. You would just look at the number of items the person finished. You wouldn't even worry about number right. Obviously, most tests lie somewhere on the continuum. There's usually some kind of time limit on any power test, and the more you kind of collapse that time limit down, the more you can introduce speed as a secondary factor of what you're measuring. So a test that's challenging to finish on time is some combination of speed and power, and sometimes you'll see diff from that. Okay, so where does diff come from? And this is a really hard question to answer. One of the places, though, it can come from, not typically, but one of the places it can come, you should be aware, is that there's unreliability in the diff indices. So the test we use, and we'll get into this in the next unit, but the tests we use to measure diff and test for diff are significance tests, typically speaking. And significance tests that work just like a t-test or an ANOVA do. They tend to be strongly affected by things like sample size. So one of the areas some of my research has been in is looking at one of the tests called the likelihood ratio test and how it's impacted by sample size. They're also prone to type 1 and type 2 errors, just like any other statistic is. So there's going to be some unreliability in the diff indices. So you can see some diff sometimes just by type 1 and type 2 error alone. So for that reason, you can choose to do things like Bonferroni corrections. It's not very common, but you could do that if you wanted to. So there's some instability and sampling error and all those kind of things that impact any statistic can also impact your diff test and any invariance test. And that's not altogether common in the invariance literature. I think in the past in the invariance literature, if you go back like 20 years, people would say if you find a lack of invariance or if you find diff, you're measuring different things here and you really can't compare the groups. And it was only after some time that people started understanding that, well, these are statistical tests and they're affected by power and all these other things. It's like a t-test. And so that's kind of where I went with my research into looking into things like effect sizes, right? So like with the t-test with 1 million people, it's probably going to be significant, but is it practically meaningful? That's where you look at the effect sizes. And we'll get into that a little bit later on, a couple lectures down the road. So if you want to know where diff comes from, so one thing we mentioned was kind of, general statistical issues, but the other thing, and probably the most relevant one, is understanding where it comes from in the items themselves. So one of the first items I showed you, I would argue it's relatively obvious with the gender bias example in the hunting and fishing, but a little bit less so with the use of negatives. And so, how do you know whether you have diff that's meaningful or where the diff came from? And the truth is, a lot of times you don't know. One of the things you can do, though, one of the strategies is separate diff items and non-diff items into their relative piles. And you look for patterns in the diff items. So the example I gave you, the first grade item, if you saw, a lot of different items that use negatives and they all tended to have diff, then that would be a pretty good way to isolate that as sort of the cause of diff and where it comes from in the measurement process. A lot of times, though, there's not going to be patterns there, and it's kind of hard to predict. And one of the things that's sort of you kind of get from other fields of psychology, like cognitive psychology, is that people are really, really good and seem to be almost kind of pre-wired to explain the situation that they're in, right? So people try to make sense of chaotic and nonsensical situations. They try to impose some kind of structure and order onto data and systems that may or may not, have order in them. And that's true here as well. When you're looking at diff items, you're almost always doing it post hoc, right? You're typically looking at items after you have found diff and trying to explain it away. And there's a couple of great stories, and I think a lot of researchers have experienced this, but there's a couple of kind of well-known stories that illustrate sort of how prone to error this is. And in one story, a group of researchers were sitting around looking at a group of four or five diff items and came up with this really elaborate explanation for, this is why this is happening. Oh my God, we should have seen this coming ahead of time. It's pretty clear that, this whatever it was is causing the diff in this case. And as they're about to kind of close the book on this, they realized they were actually looking at the wrong items. And the items they were looking at didn't have diff at all. And so I think people are really prone to that. So I would caution you a little bit about trying to look at items after the fact, after you've found the diff already, and trying to explain why it's there, because that's something that people are really good at coming up with explanations for. But sadly, of course, that's not the way science works. You want to make your hypotheses beforehand and then test those hypotheses empirically as a much more rigorous approach. Lastly, I would say that one of the things that a lot of testing companies do is they do an a priori item review. So instead of doing it after the fact, they actually do have experts review the items to find out whether or not there's going to be any bias in them. So way back when I worked at SHL before I came to NC State, they had this. They would send off items to a so-called expert. on gender issues, racial issues, what have you, and the expert would look at the items and say, I think this item here may cause some differences in this group, or it may not be seen and read in the same way by this group, yada yada. And that's pretty common to do. The problem is it doesn't seem to be very effective. The few studies that are on this, and there's really not many, have typically found virtually no relationship between items that experts say ahead of time will have diff and the items that actually have diff. Very little, maybe no correlation in a lot of cases here. So this is, it's something that's done a lot. It might be done more for optics than it is for any kind of scientific merit, but it is a tool that psychometricians have that testing companies in particular, will often look at.